All right, I must say, when I was invited to give a talk here at this workshop, I was a bit surprised because I'm not at all an expert in Bender's decomposition. So don't expect any methodological contributions or tricks or tweaks in your implementation, all that kind of stuff. I'm kind of hoping that, well, at the end of a long day, you're no longer in need for that. So what I do plan to do is talk about a fun application, sports scheduling, and how Bender's decomposition helped. Of course, I need to credit my co-authors, David van Bulk, who is actually also here, who did actually most of the work on the Bender's decomposition, and, well, Frits Pieksma, who, well, together with me has been scheduling, is still scheduling the Belgian soccer professional leagues since 15 years or more. All right. So, in essence, what's the sports scheduling problem? Well, you are given a set of matches, and you're given a set of rounds or time slots. And you need to decide which matches are to be scheduled on which rounds. Okay? I'll go through some terminology first, pretty basic, but still. A match A versus B is played at the venue of the home team, A, and with the opponent, B, being the away team. I have learned that in the US, it's actually the other way around. They put the away team first and then the home team. But so the home team comes first. If a team plays 2 consecutive home games, it's said to have a break. It breaks the regular pattern of home, away, home, away. So 2 home games in a row or 2 away games in a row is called a break. If on a round you don't play a game, you have a bye. If your number of teams is odd, of course, this is going to happen. Okay. The focus of today is on the so-called round-robin tournament, double round-robin tournament. So each team plays twice against each other team, once at home, once away. And there are other tournament formats, but from a scheduling perspective, this is, I guess, the most interesting one. And it's also a very popular one. Okay. There are 2 crucial constraints. A team can play at most 1 game per round. A round is typically a weekend or time slot. And, of course, all matches need to be scheduled. We are not going to tolerate any deviations from these 2 constraints. Now, there are 2 types of schedules. A time-constrained schedule is a schedule that uses the minimal number of rounds that you need to schedule all these games. Right? So you see an example here for a double round-robin tournament with 6 teams, labeled A to F. So every team plays twice against every other team, so even every team has 5 opponents. So every team will play 10 games. So it's easy to see that you need at least 10 rounds, and that's what happens here. So this is a time-constrained schedule. There are also time-relaxed schedules. In a time-relaxed schedule, you use more rounds than what you actually need. Like, for instance, here, it's the same tournament, the same teams, but now we've used 13 rounds. This is, well, not uncommon in sports in the US, for instance. NBA is organized in this way, and so on. It's less common in European football, but it happens. Okay. Is this at all difficult? That's a question that I often get when you talk about this topic. Is it actually difficult? I mean, who does research on that? It was solved in 1847 by this guy, Reverend Thomas Kirkman. He came up with this paper on a problem in combinations. He developed a method known as the clock method that allows you to produce a schedule for a round-robin tournament. Now, the more critical minds in the audience may think 1847. There were not so many sports around in 1847, and also not so many tournaments. And you would be right, because of course this paper is not about sports. it's actually about what they call the schoolgirl problem. Apparently, in 1847, that was the problem that people studied, the schoolgirl problem. It's the following. There is a school. There are 15 schoolgirls. They leave the school every day. In those days, you went to school 7 days a week, apparently. So they leave the school in rows of 3. And they want to do that each day in a different way, such that at the end of the day, at the end of the week, you have been walking next to everyone. A variant of that problem happened yesterday evening for some of us at the dinner, where we were also being seated with as many partners as possible at the table. Anyway, later it turned out that this solution for the schoolgirl problem actually solved the sports scheduling problem. It's actually quite simple. This is the clock method for 8 teams. So there is one team, number 8, here in the middle, the other ones around it, and these edges here indicate which teams play against, well, each other. So you start from this organization, and you each round just tilt all the edges one click to the right, and you have your next opponent. If you keep doing that for every round, in the end you will have a feasible schedule. Right, a schedule that respects the 2 crucial properties. Every team plays at most once per round, and at the end you will have seen every team once or twice, depending on what you need. Okay, so that is easy. However, finding a good schedule, that's the real challenge. Because in practice, there are lots of things that play a role. Right? If you talk to clubs, they will tell you that it matters that not all schedules are equal. They will want a schedule where they start the season with a home game against a weak team. It's always interesting to hear from these teams what they think is a weak team. Opinions differ. On some rounds, it could happen that their stadium is not available or not fully available, or that their parking lot is not available, so they're not able to receive as many fans or eaters or as normal. So on these days, they prefer not to play a home game, or they prefer to play a home game against a team that doesn't bring many fans anyway. Some teams share a stadium. And so on. It matters. Let me give you a hint on this. These are some numbers on the total attendance per season in Belgian football. Right? So overall the games. And here per game, because the number of games has changed over the years. So, in blue, the years before Fritz and I entered. In red, after. Of course, this is not a scientific proof, but I like to think that it matters, that you can boost stadium attendance by making a proper schedule. TV broadcasters. Also, they have lots of constraints. I don't know if it's known in the Netherlands, but in Belgium there is something like a Super Sunday, which is a Sunday which has 2 top games, broadcasted one after the other. They like that, the Belgian broadcasters. They think they have more people watching in this way. They want to broadcast the top games on the best time slots. They want the decisive games at the end of the season. So they have lots of these constraints. Again, TV broadcasters pay for their product. They pay for the right to broadcast. They actually also pay for the schedule. These are the amounts that they pay in Belgium over the years. And you can see it's steeply increasing. And again, I like to think that the schedule has contributed to this. Unfortunately, we are not paid any percentage of this amount. But still, yeah. For some reason, football is linked with hooligans, right? People who prefer to come for a good fight, even at young age, and even if they're a Feyenoord fan, I believe. So there is police needed, and police, they have preferences about when games are scheduled. So if you can imagine if there is some politician visiting the country, or if there is a big pop concert or anything else that needs police attention, well, you would not want to add a risk game on top of that, right? And at least in Belgium, the mayor or the police has the right to forbid a game, so you need to take that into account when making the schedule. There are some teams that share the same police zone, so in that case it's a capacity problem. The police cannot handle too many games in the same zone at the same time. So also there are constraints. And again, I have some numbers here. This is the police force needed per match. Apparently this has been a question in the Belgian Senate that comes back every year, like how much are we actually paying for all this football stuff? And then they have to report how many police officers spend their time, supervising these games. So that's where we get the numbers. And blue, should I remind you, is before we were involved, red is after. So you can make a difference here. So even if you don't like sports or football at all, you are paying for this, right? You are paying for the police, so you should be happy with the kind of research that we are doing. And then there are still some general fairness issues, right? No team starts the season with 2 home games. That's considered unfair. No team ends the season with 2 home games. You shouldn't play too many strong teams in a row. You should also not play more than not play 3 or more away games in a row, especially in the start of the season. First 6 rounds, there should be a balance in the opponents that you see. Should be at least 6 weeks between a game, A against B against A, just to allow the hooligans to cool down. That kind of constraints. So, if you take into account all these constraints, it's a totally different matter. Then it is a difficult problem, extremely difficult, I might add. There are some complexity results saying that if some games cannot be scheduled on some rounds, it's NP complete. You will also be in trouble finding a constant factor approximation in that case, unless P is in P. If you only consider travel constraints, like in the traveling tournament problem, if travel is all that matters, forget about all the other ones, then at this point we are not able to solve some instances with just 12 teams. 12. If you look at only carryover effect is a kind of fairness measure, which has to do with the previous opponent of your opponent, right? If you want to balance that in a fair way, well, that is a very difficult problem. It's unsolved until now for just 12 teams. If you only care about minimizing the number of breaks, remember a break is when you play 2 home games in a row or 2 away games in a row. If you only want to minimize that, well, there are still instances around with just 10 teams that have been unsolved until now. So it's pretty difficult. And in practice, there are lots of constraints. Real-life problems have lots of constraints. Some of them hard constraints, most of them soft constraints, because in the end they are conflicting, so you have to make some trade-off. David and myself and 2 other authors have made an overview of the constraints that we find in the literature. Right? We tried to classify them, and we came up with 19 types of constraints, where, for instance, the CA1 would be a constraint that says this team cannot play a home game on this particular round. Right? That would be a type of constraints, and we have 19 of these types. Actually, that brings me to the Robin X project, which is actually a great starting point if you want to get involved in sports scheduling, or if you want to offer some topic to a master thesis student or something like that. And I would advise you to go to this website. We have this tool here where you can indicate what kind of constraints you want your problem to have, and which kinds of constraints that you hate. And then you can click search and you get a list of all the papers in the literature that have problems with exactly these properties. So you would easily find the relevant literature. Even more, there is also a repository of problem instances. So for, well, almost all problems that we could find, we have a file that you can download with all the details of the instance. Also an indication of what kind of constraints play a role, what's the best found solution so far, what's the best bound history of solutions, and whether or not it has been solved to optimality, right? So that's a, I think, great starting point for if you want to dive into sports scheduling. Okay, now, part 2, vendors. Of course, you can try to tackle this sports scheduling problem by making one big IP model, right? All around this variable xijk, which is 1 if team I plays a home game against team J on round K, and 0 otherwise, right? You could do that. Now, I wish you good luck, but that's not going to work. I mean, you're not going to get anywhere with this kind of problem. Then what? Well, there is this insight that a schedule actually consists of 2 components, right? This here is a schedule. It tells you on round 1, team 1 plays at home against team 3, 4 at home against 17, and so on. This schedule is actually the combination of an opponent schedule, right, which tells you for each team what the opponents are in the various rounds, and a set of home-away patterns, right? This shows you for every team whether it plays home or away for every round, okay? If you merge these 2, you get the schedule, okay? Now, this has been used by Nemhauser, who we now know as the person with the strange accent, and Trick, in their well-known first breakdown schedule approach. So they say, well, you should first construct a suitable set of home-away patterns, right? You should first come up with this. And then, based on that knowledge of who plays home and who plays away, you find the opponents in the second phase. Okay? Now, there are 2 problems here. First of all, not just any set of home-away patterns leads to a feasible schedule, right? There are some obvious necessary conditions. Of course, every round should have the same number of homes as aways, right? Otherwise, it's not going to work. Also, every home-away pattern should be different. If you have 2 identical home-away patterns, well, these teams will never be able to play against each other, right? They will each time have both home games or both away games. You cannot match them. Now, in 2003, Miyashiro and others came up with a condition, a necessary condition, where the idea is mainly look at any subset of the teams and go over all the rounds and count the number of matches that you could potentially schedule between that subset of teams. And that should be at least the number of mutual games that this subset of teams plays, right? Otherwise, you're dead. Now, that condition is necessary, but has been shown later not to be sufficient. Then Dirk Briscorn came, and he proposed an IP formulation to check whether a given pattern set is feasible. And that IP formulation maximizes the number of games that you can schedule given the home-away patterns. And he said, well, a necessary condition would be that the LP relaxation of that IP gives you the number of games that you need to schedule. Right? So it's conjectured by Briscorn that is actually a sufficient condition, but so far not proven or disproven. Okay. Now there is a second issue. Once you have a home-away pattern set and you have been able to compute an opponent schedule, well, suppose that this schedule is not to your liking, it's not optimal, it's not good. Well, how do you change the home-away pattern set, right? How do you backtrack? Or even if your home-away pattern set is not feasible, how do you improve it? So that's the second issue, and it will come as no surprise that this is where our friend Benders comes in. So for a long time, this first break then schedule idea was basically run with some kind of complete enumeration without a real backtracking. But in 2008, Rasmussen and Trick came up with this logic-based Bender's guts, where the idea is, well, they start from generating a set of patterns using an IP, and they check whether that pattern set is feasible using constraint programming. Or they also have a heuristic to quickly check feasibility. Right? If it turns out infeasible, they add a cut. If it is feasible, they increase the upper bound to get better pattern sets in the next round. And the logic-based cuts that they used were based on pattern diversity, more or less like the Miyashiro constraints that I showed you on team allocation and on game separation, how many games there should be between A and B against A. Now, this is nice, but also a bit limited. It works only for minimizing the number of breaks, and it takes into account just two types of constraints, venue availability and game separation. And you remember that there is this long list of constraint types in sports scheduling. But it's a very nice first step. Together with David, recently we developed a more traditional Bender's guts formulation for this problem. Okay, so here's the IP model, the full IP model with two basic variables. We have the HIRs, which is, well, HIR is 1 if team I has a home game on round R, and 0 if it has an away game. And XIJR is still 1 if I plays at home against J on round R, 0 otherwise, right? And then we have an objective function that consists of, well, a component related to the home away patterns, to the H variables, and a component related to the opponents, to the individual games. And we have lots of constraints, constraint linking the home away pattern to the games that you can play. I mean, you can only play at home if your home away pattern says that you have a home game. And then constraints saying you can play every opponent meet once at each venue, and you can play exactly once per round. And there are lots of other constraints, but I didn't put all them here just for convenience. Now, this is going to be my master problem. So in the master problem, I focus on the home away patterns. So I keep the H variables that determine whether or not you play home. And I project out the XIJR variable. So we change again. Now the X go again to the subproblem. So the subproblem checks whether there is a feasible schedule given the home away patterns. Now, recall Briscorn's conjecture stating that the LP relaxation is actually a sufficient condition to know whether it's feasible or not. We're going to use that, of course, by checking whether the LP relaxation gives you a compatible opponent schedule. If not, we add the Bender's feasibility cut. If it does, and we have underestimated the cost of that solution, we add a Bender's optimality cut to the master problem. Of course, if at some point we find this solution, we are still going to check whether there is we are still going to check the IP to find out whether there is a compatible opponent schedule. If that IP turns out infeasible, we add a no-good cut or a strengthened no-good cut. In the other case, we add an integer optimality cut, right? And, compared to the previous implementation of Bender's decomposition, the logic-based Bender's decomposition, this gives us a bit more flexibility to take into account this wide variety of constraints. I mean, as long as you can formulate them as an LP, it's okay. And that is good enough for sports scheduling to get most of the relevant constraints. Okay. There are still some extensions because, if you really have lots of constraints, which happens in practice, then solving this IP is really the bottleneck, right? You're not going to be able to do that, at least not very often. So in this first extension here, we changed the strategy a bit. We developed what we call first break heuristically schedule. And we replaced this IP with a variable neighborhood search, right? So the idea is that this part of the Bender's decomposition generates a bunch of promising pattern sets. And then we feed that bunch of pattern sets to a variable neighborhood search to get decent solutions. Keep in mind that, in practice, we are, this is a heuristic, right? We're not really looking for any optimal solutions or proven optimality for real-life problems. That's not really what we are looking for. Okay, and a second extension is, well, how to deal with these time-relaxed schedules. These schedules where you have more rounds than you actually need, and where in some rounds, some teams don't play. They have a bye. Well, in that case, the home-away patterns don't work very well anymore, and we replaced them with a similar idea, the game off-day pattern, right? Which indicates whether you play a game with a G, or whether you don't play. You have an off-day, you have an O. That's a GOP pattern. So here you see a pattern for team 1, which has a game on the first round, another game on the second round, doesn't play on the third round, and a game on the fourth round. And this is a possible schedule. There are multiple possible schedules corresponding with this set. So it could be that team 1 plays against 2 in the first round, and then plays against 3 on the second round, and then again against 4 on the final round. So replacing these hop sets by these GOP sets helped to deal with the time-relaxed schedules, or also with a situation where your number of teams is odd. All right. Let me conclude with some success stories. Okay. Back to the traveling tournament problem, which is the sports scheduling problem where we only look at distance, only look at travel distance. We want to minimize the travel distance that the teams have to cover during the tournament. There we looked at a special case where all the distances are equal. We were able to find optimal or new best solutions for all but 2 instances known in the literature, up to 30 teams. If you only care about optimizing the rest times, the absolute rest times. Now we are talking about a time-relaxed schedule. Your rest time could be long or short, depending on, well, you have many games close to each other or not. So if you want to optimize the rest time that you have in between games, well, we got excellent results. In particular for competitions that are somewhat similar to the NBA or the NHL, up to 20 teams. Now, the first 2 are maybe not so surprising because if you think about it, the objective function here is all determined by the home-away patterns or the GOP patterns, which we deal with in the master problem. The bottom one, where we optimize rest differences, is different because there you have to know your opponent. Rest difference, well, you look at how many games your opponent has rested and how many, days you have rested, and the difference between that is called unfair, right? If your opponent has rested more than you, it's unfair. So we want to minimize this difference in rest time here. And of course, for that, you need to know the opponent. So you have to look at the subproblems too. They also determine the objective function. But also here we have optimal and new best solutions for all instances in the literature up to 16 teams. Okay, but these are kind of theoretical problems and still very specific problems because they deal with only a very limited number of constraints. There are also general sports scheduling problems that have a bunch of real-life constraints. And a couple of years back, we organized the international timetabling competition on sports scheduling. And that competition had 45 problem instances, which were challenging, realistic, and diverse. And later, we added 518 additional instances, similar. And that competition had a lot of participants. So there were lots of people that developed an algorithm to solve this bunch of instances. Actually, you will notice that there are some familiar names here because Eindhoven University also participated in this contest. So the idea was, can we develop a general sports scheduling solver that can handle this wide variety of constraints. And, well, we did not participate in our own competition, would not be very ethical, I guess. But later, when the competition was finished, we applied the first break heuristically schedule based on the Bender's decomposition to this set of instances. And this was the result. Now, you see the instances here. They have been using principal component analysis plotted on a 2D scale so that the more similar instances are grouped together. And from the colors, you can see which algorithm had the best solution there. So the Bender's decomposition is this one, first break heuristically scheduled, so the purple one. So you see that we had quite a bit of instances where we scored best. And this is what they call algorithm footprint. So you can see that in this range of the instances, we score quite well. And here we don't score quite well. And of course, that depends on the constraints that are present, right? The instances differ in the constraints that appear. And not all algorithms handle all kinds of constraints equally well. So we scored well in this corner here. If we would have participated, we would have ranked 4th in the final ranking, which is not bad. I mean, we had 10 instances where we had the best solution. We also had a number of instances where we didn't find the solution at all. So that's not so good. But in any case, look who ended 7th. We would have beaten them. So that's already worthwhile. The final application is real life, right? As I told you, together with Fritz, we have been scheduling the Belgian Pro League for many years. And that's not just one competition. There is the Jupiler Pro League, which is the top competition, the professional competition, with 16 teams, and they play 30 rounds. But there is also the Challenger Pro League, which is the second professional competition. And then you also have Voetbal Vlaanderen, which is the Flemish amateur, top amateur competition, and ACFF, which is the Wallonian top amateur competition. So we actually have 4 competitions that we schedule. And while in the old days, you could schedule them hierarchically, you could say, well, I'm going to schedule this one first and then care about this one, then this one, this one. That's no longer possible because these competitions are very heavily linked. There are teams, well, it could happen that a team shares a stadium with a team in a different competition. And since a couple of years, the under 23 teams have been added to the professional and amateur competitions. So almost every team in the top league has an under 23 variant in one of the lower competitions. And again, they should alternate, right? If one team plays at home, the other one cannot play at home. So there are many links between all these competitions that prevent a hierarchical approach in this problem. You have to solve them all together, right? So basically what we are doing now is coming up with 4 sets of home-away pattern sets that all result in a feasible schedule. And well, again, here we also use the Bender's decomposition. We use the Bender's cuts. Bender's cuts are mainly on the level of the Pro League because that's the highly constrained competition. That's where the TV cares about. That's where the police has to work. And that's less the case in the amateur leagues, as you can imagine. But still, there is a feasibility issue here. It has no sense that you come up with a great schedule for the first division if one of the lower leagues, well, would have something infeasible, right? They also need a schedule. So, yeah. Okay, so I briefly talked with Cor yesterday. I asked whether Professor Benders has anything with sports, and he didn't really come up with something. But still, I did learn that he cares about practice, right? And I guess he would be happy to see that his idea has made quite a difference in the practice of sports scheduling. Okay, I think this ends my talk. I have a slide with references if you want to read more. And, well, that's it.